In the immensity of the universe, a silent drama unfolds. The Andromeda Galaxy, our cosmic neighbor, keeps secrets and celestial catastrophes that shaped its destiny. Andromeda is not a simple spiral galaxy, but a colossal formation that extends over 220,000 light-years and contains 1 trillion stars. However, beneath its serene beauty hides a history marked by violent collisions and dramatic transformations. Astronomers have discovered that the double nucleus of Andromeda, a unique structural anomaly, points to ancient galactic cannibalism, when smaller galaxies were devoured to fuel its growth. In the heart of this giant, a supermassive black hole silently consumes material, affecting the destiny of all around it. Join us today on a journey through Andromeda's hidden catastrophes. We will explore its turbulent past together and analyze its future, where a cosmic event will take place that will forever change the very structure of the universe, transforming our world. At the end of the 19th century, the Andromeda Galaxy was shrouded in mystery. The first astronomers who observed it through their telescopes saw it as a blurry spot of light in the night sky. Many thought it was a nebula within our Milky Way. The first great advance in understanding it came with the arrival of more powerful telescopes in 1885. From the Lick Observatory in California, they made a surprising discovery. They observed a new bright star near the nucleus of the Andromeda Galaxy, which they called S Andromeda or supernova SN 1885. It was an extraordinary event, as it was the first time that a supernova had been observed outside of the Milky Way. The sudden brightness was a beacon that shattered the misconceptions of the time. However, confusion arose at first. Could it be a nova, a typical phenomenon of our galaxy, or are we talking about something more substantial? The light curve of SN 1885, it revealed its true nature. Unlike novae, which fade relatively quickly, the brightness of this supernova persisted for months, indicating a cataclysmic explosion, a distinctive sign that signaled the death of a massive star. Through careful analysis and advanced models, scientists reconstructed the event. They believe that SN 1885 it was a Type 1a supernova, a thermonuclear explosion of a white dwarf star in a binary system. The explosion was so powerful that it temporarily eclipsed the entire Andromeda Galaxy. The observations of SN 1885 it had profound implications. They represented a turning point in astronomy, laying the foundations for the hypothesis that there are other galaxies composed of the same stellar phenomena as ours. The discovery paved the way for the later work of Edwin Hubble, who confirmed that Andromeda was indeed an independent galaxy and not part of the Milky Way. Today, thanks to a discovery made more than a century ago, we understand that supernovas are crucial elements in the life cycle of stars, scattering heavy elements throughout the universe and allowing us to better understand the dynamic nature of galaxies. Thus, Andromeda, which extends along 260,000 light-years, houses a great variety of celestial phenomena, especially in its central region and in its spiral arms. The central region of the galaxy is a very busy hub of activity. It houses a large concentration of stars, gas, and dust. In its center is a supermassive black hole, but the region is also characterized by a prominent double nucleus, an unusual feature that distinguishes Andromeda from many other galaxies, but we will talk about it later. One of the most exciting aspects of the central region of Andromeda is the ongoing star formation, despite the presence of a supermassive black hole. The nucleus of Andromeda is a cradle of new stars. Areas of dense molecular clouds collapse under gravity, initiating nuclear fusion and giving rise to new stars. These stellar incubators are very important to understanding the life cycle of stars and the evolution of galaxies. The spiral arms of Andromeda are impressively complex. These arms are scenarios of intense star formation, where young massive stars illuminate the surrounding gas clouds, creating regions known as hydrogen-2 regions. These regions are ionized by the ultraviolet radiation of the hot young stars, which makes them shine intensely. However, the spiral arms are not static, but dynamic structures influenced by the gravitational interactions and the rotational forces of the galaxy. As the gas and dust move through the arms, they encounter shock waves that compress the material and trigger further star formation. This cyclical process keeps the arms alive and full of young stars. However, in the vast expanse of Andromeda, some stars play a crucial role in our understanding of the cosmos. Among them are the Cepheid variable stars, which change their brightness and provide information about stellar processes and cosmic distances. In 1923, Edwin Hubble, using the 100-inch Hooker telescope at the Mount Wilson Observatory, observed a star in Andromeda that forever changed our vision of the universe. This star, later named M31V1 and known as Cepheid variable star, plays a fundamental role in astronomy, since its predictable changes in brightness make it a reliable standard candle for measuring cosmic distances. Before Hubble's discovery, the nature of spiral nebulae like Andromeda was the subject of heated debates. In 1920, Harlow Shapley and Heber Curtis debated whether these nebulae were part of our Milky Way or separate galaxies. The dispute remained unresolved until Hubble identified M31V1 as a Cepheid variable in 1923. The discovery of the relationship between the period and the luminosity by Henrietta Swan Leavitt. The relationship shows that the greater the period of variation in brightness of a nebula, the greater its intrinsic luminosity. By measuring the period and apparent magnitude of M31V1, Hubble was able to calculate its absolute magnitude and, therefore, the distance to Andromeda using the formula. Hubble determined that M31V1 was almost 1,000,000 light-years away, far beyond the Milky Way. This revolutionary discovery confirmed that Andromeda is an independent galaxy, which greatly expanded the known universe. Both amateur and professional astronomers continue to observe M31V1 and other variable stars with modern equipment. Modern CCD cameras, more sensitive than the photographic plates used by Hubble, allow even amateur astronomers to replicate Hubble's work. Variables like M31V1 remain vital tools in cosmology to this day, as they help astronomers measure distances to distant galaxies, calibrate other distance measurement methods, and refine our understanding of the scale and expansion of the universe. In addition to the variables, other variable stars exist in Andromeda's spiral arms, including the W Ursae Majoris stars. These stars also serve as standard candles. Although they are less bright than the Cepheid, their study provides additional clues about the structure and mysterious history of Andromeda. And now, something equally interesting. Our closest galactic neighbor holds secrets that have baffled astronomers for decades. Among its many mysteries, two stand out: a double nucleus and the behavior of the central supermassive black hole detected in high-resolution images. The nucleus of Andromeda presents a unique mystery. Unlike most galaxies, which have a single central nucleus, Andromeda has two bright nuclei. This unusual structure has led scientists to propose various theories. One of the main hypotheses suggests that the double nucleus is the result of the merger between a smaller galaxy and Andromeda. As the nucleus of the smaller galaxy curves inward, two bright centers appear. The Hubble Space Telescope provided the first detailed images of this double nucleus, showing dense star clusters around each nucleus. Subsequent observations from the Chandra X-ray Observatory and the Very Large Telescope expanded our knowledge, showing that one of the nuclei is probably the original nucleus of Andromeda, and the other a remnant of a captured galaxy. In the center of the galaxy is a supermassive black hole with a mass millions of times greater than our Sun. Recent research using data from NASA's Spitzer Space Telescope has shed light on the feeding habits of this colossal entity. Unlike the chaotic food consumption observed in other galaxies, Andromeda's black hole quietly feeds on streams of dust and gas extending thousands of light-years away, continuously feeding it. These spiral dust currents, similar to water drainage, maintain a continuous but smooth flow of material toward the black hole. Computer models suggest that this constant flow avoids the large luminosity fluctuations that usually characterize black holes that absorb matter in clumps. Instead, The matter forms a small disk of hot gas that gradually falls toward the black hole, keeping it relatively calm. Ongoing research, combining data from multiple telescopes and advanced simulations, continues to unravel the unique structural characteristics and enigmatic behavior of a nucleus, revealing the complex and fascinating nature of our neighboring galaxy. Andromeda has a rich and dramatic history that has shaped its current structure. Recent studies show that Andromeda's formation was marked by significant events. First, a massive burst of star formation laid the foundation for the galaxy, followed by a second wave of star formation caused by a large-scale wet merger, the collision of two gas-rich galaxies. Galactic archaeology has helped scientists in this task, which consists of studying ancient stars to understand the galaxy's history. By analyzing the chemical composition and movement of these stars, scientists can reconstruct the past events that shaped the galaxy. In Andromeda's specific case, the presence of ancient stars with different chemical compositions provides clues about its turbulent past. Andromeda experienced two distinct eras of star formation. The first era resulted from a rapid accumulation of gas that gave rise to a thick disk of stars. The second era, which took place between 2 and 45 billion years ago, was most likely caused by a wet merger that gave rise to a thinner and younger disk of stars. Over billions of years, Andromeda has grown by swallowing more than 100 satellite galaxies. This process, known as galactic cannibalism, has significantly affected its structure and star formation. These interactions not only increased its mass, but also triggered new waves of star formation. One of the most dramatic events in Andromeda's history was the collision with a compact elliptical galaxy, M32. This collision profoundly affected Andromeda's spiral arms and overall structure. The gravitational interaction caused by M32 created waves and deformations in its disk. The collision with M32 caused significant disturbances in Andromeda's spiral arms, leading to its current structure. These interactions likely triggered bursts of star formation, creating the bright young stars still observed in the spiral arms. Andromeda is surrounded by numerous satellite galaxies, each playing a role in its evolution. In addition to M32, the second most important companion is NGC 205. Interactions with them have left remarkable traces on Andromeda, including gravitational deformations and tidal currents. However, Andromeda's history is still unfolding, since it is on a collision course with something less abstract and more dear to us. This future collision will lead to the formation of a new galaxy that will radically change our past forever. In about 45 billion years, a tremendous cosmic event will occur. The Andromeda Galaxy and the Milky Way will collide. This imminent merger will forever change the structure of both galaxies, leading to the formation of a new elliptical galaxy. The Andromeda Galaxy is currently moving toward the Milky Way at about 68 miles per second. This head-on collision is an uncommon event affected by the gravitational attraction between two massive bodies. Although the distances are enormous, the galaxies are destined to merge. The collision of the Milky Way with Andromeda will not be a sudden impact, but a very long process lasting several billion years. First, the galaxies will pass through each other, and their gravitational forces will create tidal distortions. As a result of this interaction, stars and gas will escape from both galaxies, forming long tidal tails. After the first pass, the galaxies will continue to interact until they eventually become a single, more stable structure. The process will lead to the formation of a new elliptical galaxy that scientists have already named Mila or Milgromeda. The merger will cause the dissipation of the spiral arms, transforming the galaxies into a more homogeneous ellipsoidal shape. Although the merger will radically change the structure of galaxies, the vast distances between stars make direct collisions unlikely. However, the solar system will be affected by new gravitational forces and could be thrown into another region of the new galaxy or even expelled into intergalactic space. At the time of the merger, the Sun will have become a red giant, which will make Earth uninhabitable. Long before that, The increasing luminosity of the sun will cause radical changes on our planet, probably depriving it of its atmosphere and oceans. Therefore, with very few remains of humanity or any other life on Earth, the direct impact of the collision will be minimal. The imminent changes lead us to consider the future of humanity. As our understanding of cosmic events increases, so does our ability to adapt and explore. The merger of Andromeda and the Milky Way may inspire future generations to find new homes among the stars, advancing our journey into space, which always leads us to reflect on our place in the universe and the future of human civilization. How will we adapt to these changes? What measures can we take to ensure our survival and continue exploring the universe? As we continue to learn from the stars, we remember the incredible forces that shape our galaxy and the limitless possibilities that the future holds for us. Let's imagine a colossal object 6 million kilometers wide hurtling through space at 12 million kilometers per second toward Earth. It is not science fiction. 66 million years ago, an asteroid like that crashed into what is now the Yucatan Peninsula, forming the Chicxulub crater and triggering a mass extinction. Today, our planet continues to be threatened by near-Earth objects, including asteroids and comets whose orbits take them into our near space. NASA and other space agencies have made significant advances in tracking and understanding these potential threats, but the risk remains. Work is being done with advanced technology to monitor and mitigate these threats, from kinetic impacts to gravitational tractors. Humanity is developing strategies to protect our world from these stellar invaders. But what would happen if another asteroid the size of Chicxulub was on a collision course with Earth today? How prepared are we for such a catastrophic event? Join us to learn about planetary defense vaders. But what would happen if another asteroid the size of Chicxulub was on a collision course with Earth today? Are we prepared for such a catastrophic event? Join us to learn about planetary defense, history, science, and the future in the face of such impressive threats. 66 million years ago, an event occurred on Earth so catastrophic that it changed the course of life on the planet. The asteroid, about 6 m in diameter, crashed into the Yucatan Peninsula in present-day Mexico, forming what we know today as the Chicxulub crater. The immediate consequences were apocalyptic. The collision released energy equivalent to billions of nuclear bombs, caused forest fires and tsunamis, and launched enormous amounts of debris into the atmosphere. The most significant and lasting effect of the impact was the release of dust, soot, and sulfur aerosols into the atmosphere. These particles created a global cloud that blocked sunlight for a long period, a phenomenon known as impact winter. New research has shed light on the fundamental role of fine dust particles in this cataclysm. A study published in Nature Geoscience in October 2023 found that fine dust, particularly particles between 0.8 and 8 micrometers in diameter, played an important role in abrupt climate change. The researchers collected rock samples 66 million years old in North Dakota, a considerable distance from the impact site, containing surprising amounts of these fine dust particles. These particles remained in the atmosphere, forming a dense cloud that persisted for up to 20 years, with the first 5 to 8 years being the most severe. This long period of darkness caused a significant drop in global temperature, estimated at more than 18 degrees Fahrenheit, 10 degrees Celsius in the first year alone, as sunlight was blocked and photosynthesis stopped. Plants, unable to produce food, began to die. This collapse of plant life had a chain effect throughout the food chain. Herbivorous dinosaurs, which depended on plants for food, faced starvation. Consequently, the carnivorous dinosaurs that fed on them also died. This chain reaction led to the extinction of approximately 75% of all species on Earth. Interestingly, the new study highlights the hitherto unknown impact of dust compared to soot and sulfur, which were previously considered primarily responsible for the prolonged cooling period. The findings suggest that, while soot and sulfur blocked sunlight more effectively, the large amount and persistence of dust had a profound and lasting impact. The study also provides information on how some species managed to survive this dark period. Hibernating plants and animals had adaptations that allowed them to survive the prolonged lack of sunlight. However, the study rules out the survival mechanisms of freshwater organisms, indicating that more research is needed to fully understand the specific mechanisms of death after a Chicxulub impact. So, what are near-Earth objects in EOs? EOs are asteroids, comets, and other celestial bodies whose orbits bring them close to Earth. These objects vary in size, from small, harmless rocks to massive bodies capable of causing large-scale catastrophe. Asteroids are the rocky remnants of the early solar system found primarily in the asteroid belt between Mars and Jupiter. Comets, on the other hand, originate in the outer regions of the solar system and are composed of ice dust and rocky material. As they approach the Sun, they develop comas and luminous tails. The danger posed by these objects depends on their size and trajectory. Although most NEOs are too small to cause significant damage, some, like the Chicxulub impactor, could cause global catastrophes. To mitigate these risks, space agencies like NASA and the European Space Agency have developed programs to track and detect NEOs. Telescopes all over the world constantly scan the sky and catalog objects that approach Earth's orbit. One of the key instruments in this work is the Wide-Field Infrared Survey Explorer, repurposed for the NEOWISE mission. Hundreds of near-Earth asteroids have been discovered and characterized by this space telescope. The role of artificial intelligence in detecting unobserved asteroids is becoming more important. In May 2024, an algorithm based on artificial intelligence, known as tranquil, less heliocentric orbit recovery, (THOR), detected more than 27,000 unobserved objects in archive images from telescopes. This artificial intelligence tool analyzes huge amounts of data, identifying and tracking objects with great efficiency. It can process up to 1,700 million points of light in a single telescope image, connecting them to asteroid trajectories. The Vera C. Rubin Observatory, which will begin operating next year, will further improve our ability to detect NEOs. Equipped with advanced artificial intelligence software, such as HelioLink 3D, this observatory is expected to catalog millions of asteroids in its first months, doubling the current known population. Although no near-Earth object is large enough to destroy the planet, asteroids larger than 1.5 kilometers can cause global catastrophes. For this reason, NASA has been tasked to detect and track these large objects. In 2021, NASA detected more than 90% of the largest objects, ensuring that none pose an immediate threat to Earth. However, smaller objects, while not as catastrophic globally, can cause significant regional damage. Take, for example, an asteroid named after the Egyptian god of chaos and destruction. It is a near-Earth asteroid that has captured the attention of scientists and the public. Discovered in 2004, this 1,000-foot wide, 304 m, asteroid initially caused concern due to calculations suggesting a possible collision with Earth in 2029. However, subsequent observations have ruled out this possibility and confirmed that APIS will safely pass our planet on April 13, 2029. APIS will get incredibly close to Earth, passing within 30,000 miles, 48,800 kilometers, of our planet. 48,300 kilometers from our planet. In comparison, this distance is less than the orbits of some of our high-altitude satellites. This very close passage offers a unique opportunity for scientific observation and research. During the flyby, the asteroid will be visible to the naked eye in some regions, appearing as a moving bright spot. This exceptional event will allow scientists to study its size, shape, and composition in unprecedented detail. NASA's Goldstone Space Communications Complex in California will play a crucial role in observing APIS using radar. Scientists hope to gather detailed information about the asteroid's surface features and rotation. In addition, the NEO mission can provide additional observations focusing on the roughness and surface composition of APIS. This data is very valuable as it will help refine our understanding of near-Earth asteroids. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, will approach APEX during its closest flyby. The goal of the mission is to study the asteroid up close, providing detailed observations that ground-based telescopes cannot achieve. OSIRIS-APEX will collect data on the composition and surface structure of APEX, as well as any changes that occur as it passes near Earth. The spacecraft's instruments will help determine the asteroid's internal composition, which will also expand our knowledge of the formation and evolution of the solar system. The close passage of APEX has also attracted the attention of international space agencies. Teams around the world plan to observe and study the asteroid using ground-based and space-based telescopes as part of the NEAT project. Researchers at the Julius Maximilian University of Würzburg have proposed several concepts for small spacecraft that could accompany APEX during its flyby. One of the proposed missions includes a small satellite that would follow APEX for 2 months to obtain high-resolution images and measurements. Another combined concept consists of a small satellite with the European Space Agency's Ramsay mission, which will provide extensive scientific observations. Although the asteroid does not pose an immediate threat to Earth, its approach in 2029 presents a significant scientific opportunity. Studying this asteroid up close will greatly improve our planetary defense strategies to protect Earth. Scientists have developed several planetary defense mechanisms, each designed to prevent potential collisions. One of the main methods is the kinetic impact strategy, which involves sending a spacecraft that will collide with an asteroid at high speed, altering its trajectory. This method is based on momentum transfer to move an asteroid to a safer orbit. NASA's 2022 mission, Double Asteroid Redirection Test, or simply DART, was the first test of this method. DART's target was a small lunar satellite, Dimorphos, which orbited a larger asteroid, Deimos. As a result of the collision, DART's orbit was successfully modified, providing valuable data for future missions. Another proposed method is the gravitational tractor. This method uses the gravitational pull of the spacecraft to slowly change the trajectory of the asteroid over time, maintaining a stable position near it. The gravity of the spacecraft can gradually alter the object's trajectory. Although this method is still theoretical and hasn't been tested in space, it is a promising approach to address potential threats identified in advance. In extreme cases, nuclear explosions could be used to divert or destroy an asteroid. In this approach, a nuclear device is detonated at a distance from the asteroid, vaporizing part of its surface and creating a recoil effect that deflects it from its trajectory. However, this method is controversial due to the potential risks and legal implications of using nuclear weapons in space for preparing for possible asteroid impacts. International space agencies regularly conduct drills and exercises. These exercises help refine detection, tracking, and deflection strategies. Planetary defense is a global issue that requires cooperation between countries. For example, in 2021, NASA participated in an international planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. The exercise simulated the detection of a fictitious asteroid on a collision course with Earth, allowing participants to practice response strategies. As we continue to develop our planetary defense strategies, international cooperation and technological advances will play a key role in protecting our world from space threats. These cooperative efforts are essential, especially as we learn more about the nature of the objects that threaten us. Asteroids and comets are often considered distinct celestial bodies. Asteroids are rocky remnants of the early solar system, mostly from the belt between Mars and Jupiter. Comets, on the other hand, are objects from the farthest reaches of our system and are composed of ice, dust, and rocky material. However, there are also rare objects that blur the boundaries between these categories and exhibit characteristics of both. One of these objects is QN-173, discovered in 2005. This celestial body orbits like an asteroid, but behaves like a comet. Unlike ordinary asteroids, which are inert, Q-173 exhibits comet-like activity, ejecting dust and developing a tail as it approaches the Sun. Q-173 orbits the Sun every 5 years and spends most of its time in the outer part of the asteroid belt. However, as it approaches the Sun, it shows increased comet-like activity. This duality makes 2005 Q-173 an interesting object for astronomers. In the summer of 2021, astronomers using the Asteroid Terrestrial Impact Alert System in Hawaii observe an object with a comet-like tail. Subsequent observations by the L Observatory and the Zwicky Transient Facility confirmed this activity. The 450,000 m, or 720,000 kilometers in length, suggests that the object is covered in icy material that sublimates when heated by the Sun. It is this process that converts the ice directly into gas, releasing dust and creating the tail. Interestingly, the narrowness of the tail indicates that the dust particles barely leave the nucleus at slow speeds, which is a mystery to scientists, as such low speeds would not normally allow the dust to escape the asteroid's gravity. One hypothesis is that the nucleus's rapid rotation may contribute to the expulsion of dust. In addition to unique objects such as 2005 Q-173, many other near-Earth objects pose a threat to our planet. The European Space Agency maintains a risk list that catalogs objects with a non-zero probability of colliding with Earth. The list contains detailed information about the size, speed, and collision probability of each object. It currently contains more than 1,600 targets. The risk list is ordered according to the Torino scale, a logarithmic scale that assesses the risk of collision based on the size, speed, and probability of collision of objects with higher values on the Torino scale. Size, speed, and probability of collision. Objects with higher values on the Torino scale pose a greater threat. Statistical analysis of these potentially hazardous asteroids shows that, although most NEOs pose a minimal risk, some objects require close observation. For example, an asteroid's size and speed have a significant impact on its probability of impact and potential damage. Large asteroids, typically more than 1 kilometer in diameter, are particularly concerning due to their ability to cause global catastrophes. Fortunately, NASA and other space agencies have identified and tracked more than 90% of these large objects, ensuring that none pose an immediate threat to Earth. Smaller objects, while not as catastrophic, can cause significant regional damage. Events such as the Chelyabinsk meteorite in 2013 and the Tunguska event in 1908 demonstrate the potential danger of small asteroids. As we continue to discover and track NEOs and refine our planetary defense strategies, international cooperation and technological advances remain critical. By understanding the nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations. Music. Imagine a single point, just a speck of light floating in an infinite sea of darkness. It's not just a random point, it's our home, Earth. But what if we told you that this point is just a fleeting moment in a cosmic panorama so vast and complex that it defies human understanding? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now multiply that image by 100 billion. Even then, we would barely scratch the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a thread in an unfathomable cosmic web. The human mind, itself a marvel, struggles to comprehend this scale. Our brains are built to understand the elevations and slopes of mountains and the immensity of oceans. But how can we understand a structure that spans billions of light years? Today we are on a journey to explore these galactic threads, the sinuses and muscles of the universe itself. We will delve into an almost incomprehensible realm, where even light's speed seems slow. Spiders weave intricate webs, fine but strong, each thread connected to the other in a complex pattern. The architects of nature create these webs to survive, capture prey, and probe their environment. Now imagine a web woven not by spiders, but by the very fabric of space and time, a web that connects galaxies, star clusters, and dark matter in a complex network. This is the cosmic web, the great architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects united by gravity. But what gives this network its structure? The answer lies in something we cannot even see: dark matter, which scientists believe makes up about 27% of the universe. Dark matter acts as the framework on which this network is built. Although it is invisible, its presence we cannot even see. Dark matter. Dark matter, which scientists say makes up about 27% of the universe, acts as the framework on which this network is built. Although it is invisible, its presence is perceived through the gravitational pull that determines the formation of galaxies and the trajectories they follow. The cosmic web has not always been as we see it today, but has evolved over billions of years, beginning with small fluctuations in the density of the early universe. These fluctuations grew, attracted by gravity, and eventually formed the majestic filaments and nodes we see now. One of the most impressive examples of a galactic filament is the Great Wall of Hercules in the Northern Crown. This colossal structure extends over 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It is a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution, or is there a grander design at work? Scientists use a variety of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here is the Earth, a blue and green pearl suspended in the immensity of space, a planet teeming with life, from the microscopic to the magnificent. It is easy to think of Earth as the center of everything, but in the grand scheme of the universe, it is just a speck in our solar system. Earth is just one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to harbor life. The oceans, the atmosphere, the magnetic field. All these elements are in a delicate balance. If we zoom out even further, our entire solar system becomes a small point in one of the spiral arms of the Milky Way, a galaxy that is home to hundreds of billions of stars, each of which could contain its own system of planets. The Milky Way is just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment surrounding Earth. However, despite its apparent insignificance in the cosmos, Earth is unusual for one reason: it has life. It is the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes observe the most remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the Sun, that ball of burning plasma that illuminates our sky and heats our planet. It is the reason you can see these images, the reason life exists on Earth. But in the context of the cosmic web, the Sun is just a node, a solitary star among countless others. Near the Sun, we find other stars, some smaller and colder, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread joined together by gravity and dark matter. Our Sun is located in the Orion arm of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is nothing special, just one of the approximately 400,000 million stars in the vast expanse of the cosmic web. Stars like our Sun form complex nodes that connect to larger structures, such as galaxies and galactic clusters. They are the building blocks, the fundamental units that shape the network. So what powers this celestial beacon? The answer is nuclear fusion. In the depths of the sun, hydrogen atoms collide and fuse to form helium, releasing enormous amounts of energy. This energy not only powers the sun, but also balances the gravitational forces that try to compress it. This energy has far-reaching consequences. It provides Earth with the heat and light necessary for life, dries our climate systems, powers photosynthesis, and even influences Earth's climate in the long term. Understanding the sun is fundamental to understanding the cosmic web. Several missions have been launched, such as the Parker Solar Probe and the Solar Dynamics Observatory, to study the behavior of the sun. These missions provide information on solar cycles, magnetic fields, and even the future of the sun. Although the sun is a vital node in the cosmic web, which nurtures life on Earth and influences our local space environment, it is just one example in a universe teeming with stellar diversity. Each star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the smallest red dwarfs to the massive blue giants, each star is a unique knot that contributes to the overall structure of the galactic filaments. Stars are often classified by mass and brightness, represented on a chart known as the Hertzsprung-Russell diagram. This diagram shows a star's life stage and gives clues about its future destiny. Let's take, for example, a red dwarf, the most common star type in the universe. Small, cool stars, also called M-type stars, often have less than half the mass of our sun. They compensate for their lack of size with their longevity, as they burn for tens or hundreds of billions of years. Red dwarfs are frugal. They convert hydrogen to helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now let's compare that to O-type stars, the rare titans of the stellar world. These stars are over 15 times more massive than the sun and can be 1,000,000 times brighter, but they live fast and die young, often in spectacular supernova explosions. Type O stars end their lives dramatically. They collapse under their own gravity, then explode as supernovas. These explosions scatter elements like carbon, oxygen, and iron into space, which favors the formation of new stars and planets. Star clusters are like cosmic nurseries, places where different types of stars are born. These clusters serve as nodes in the cosmic web, joining different regions of the galaxy, and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different star types contribute to the cosmic web. These virtual models can simulate billions of years of cosmic evolution in weeks, showing how stars serve as building blocks of larger cosmic structures. Thus, we have discovered that stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey that spans billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity attracts these particles, which become denser and hotter until nuclear fusion ignites a new star. Once a star reaches the main sequence, it enters a period of relative stability. The hydrogen in its core converts into helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, where our sun is now. But even stars like ours must face changes. In about 5 billion years, the sun will run out of hydrogen. Its core will contract, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the star's final destiny. Depending on its mass, a star will have one of several endings. Stars with less mass, like our sun, will lose their outer layers, leaving behind a white dwarf. More massive stars can undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The agony of stars scatters important elements through space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars are an integral part of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures, but what unites these galaxies? What are the threads that weave the universe's complex fabric? The answer lies in the galactic clusters. Galactic clusters are huge collections of galaxies bound by gravitational force. They can contain only a few or thousands of galaxies and often span millions of light years. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters, even though we cannot see it. Though we cannot see it, we know it exists, as it holds the cluster together and shapes its overall structure. Within a cluster, galaxies are not static, but in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial for the evolution of galactic clusters and, by extension, the cosmic web. But clusters are not the end of the story, as they often group together to form superclusters, among the largest known structures in the universe. These superclusters serve as main nodes of the cosmic web, joining numerous clusters and filaments. Understanding galactic clusters is key to unraveling the mysteries of the cosmic web, as they serve as threads connecting galaxies, forming the paths through which matter and energy flow on a cosmic scale. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our attention to an even more mysterious phenomenon. What if there were real threads, chains of pure energy, binding the universe's fabric? These hypothetical one-dimensional defects in space-time could be the universe's loose threads, remnants of the earliest moments after the Big Bang. Let's imagine the universe moments after the Big Bang, in a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went well. In some regions, twists occurred that led to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as Earth. They would extend along the vast expanse of the universe, perhaps even from one end to another. Due to their enormous mass, cosmic strings would exert a strong gravitational pull that would affect the movement of galaxies and even bend light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues on. Scientists are using theoretical physics and observational astronomy to search for these elusive structures. If the existence of the strings is confirmed, they could become the missing links that help us understand not only how the universe is organized, but also why it is organized this way. However, let's go back to the structures of incommensurable scale, the superclusters. They're the gravitational anchors that hold together vast networks of galaxies and clusters. Let's imagine that we move away from our galaxy, the Milky Way, beyond our local group, and even beyond our local Virgo supergroup. We would find a network of superclusters, each containing hundreds or thousands of individual galaxies united in a complex gravitational dance. Superclusters are unevenly distributed, forming a kind of cosmic skeleton around which galaxies and clusters are located. This skeleton gives the cosmic network the shape that defines the large-scale structure of the universe. Within superclusters, galaxies and clusters are in constant motion under the collective gravitational attraction of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and constantly changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies, such as the Great Attractor. These are regions with such a strong gravitational force that they influence the movement of the entire supercluster, acting as axes of the cosmic network. Understanding superclusters is fundamental to cosmology, as they constitute the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. Scientists estimate the observable universe at 2 trillion galaxies, Yet what we can see represents less than 5% of the universe. At the edge of cosmic knowledge, we feel humbled by the scale and complexity of the universe, from the smallest particles to the largest galactic filaments. Each element is a piece of the puzzle here. Here we are, a pale blue dot, a mere speck in the cosmic network. But it is from this vantage point that we have begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of seeing billions of light years away, we become not only spectators, but active participants in this cosmic journey, and each new discovery is a step towards answering the eternal question that leads us all to reflect. What other mysteries does the universe hide that we have not yet unraveled? The solar system has served as a reliable laboratory for life, but one day humanity will have to abandon its native Earth to continue to exist. In recent decades, scientists have been desperately searching the dark depths of space for a refuge for life. So far, none of the exoplanets we have found has refuted the hypothesis of the singularity of life, but what if we are simply looking in the wrong place? Perhaps it is not the planets that contain all the answers, but their exomoons of mystical deep space are different from any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing characteristic. Inside them, life can be found far more often than in normal exoplanets. Today, we will immerse ourselves in the mysterious distant universe and try to discover why exomoons could one day change humanity's fate. Let's go back to the beginning of the history of exoplanet science, since astronomy received a strong boost only in the mid-20th century. Scientists began studying the first exoplanets not long ago at all. The first confirmed exoplanets were recorded back in 1992. It was a group of planets with mass similar to that of Earth orbiting the pulsar PSR B1257 plus 12. Only 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, dedicated to the study of planetary systems outside our solar system, and, in addition, to the search for places where life similar to human life could originate. They did not have to wait long. In the following years, astronomers found several more exoplanets, until in 2009 the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets with a size and conditions similar to those of Earth. Currently, we already know more than 5,500 planets outside the solar system, and it is likely that the recently sent James Webb Telescope can show us even more distant planets. In 2013, scientists were able to determine the color of the planets for the first time, and a year later, they were able to record the magnetic field and, subsequently, volcanic activity. Finally, in 2018, astronomers made a new potentially revolutionary discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. Although this may not seem like such an incredible discovery at first, exomoons open a new chapter in modern astronomy. They're not only novel and unexplored space objects so far, but also near the planet Kepler 1625b. Although at first glance this may not seem like such an incredible discovery, exomoons open a new chapter in modern astronomy, not only because they are novel and hitherto unexplored space objects, but also because they are potential elements to sustain life on exoplanets and on the satellites themselves. Each year, knowledge about distant and faint exoplanets deepens, bringing scientists closer to a complete picture of the history of the universe. But how did scientists manage to confirm so many planets in such a short time, when it is impossible to take a picture of each one? Only 69 planets have been found using images. The most popular method is the transit method, which you may already know. When an exoplanet passes in front of its central star, it becomes slightly fainter, revealing the presence of an object orbiting around it. Although this method does not allow direct observation of the planet, and may turn out to be just an error, it is currently the most effective method. The exploration of exoplanets plays a crucial role in all of astronomy and in the future of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exomoons are not of great interest to current research. The main problem with the search for these exoplanets is the difficulty in detecting them with telescope radars. Although no scientist denies that some exoplanets may have satellites, it is an extremely difficult task and, to some extent, even impossible with our current technologies. The transit method, or more precisely the method of studying the displacement of the spectrum of stars, can confirm the existence of an exoplanet, but not that of a satellite that orbits around it in almost no circumstance, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Therefore, even the first exomoon found by Kepler and those discovered later near the planets Kepler 1708b and Kepler 1513b are still not considered conclusive proof of their existence, and, therefore, there's the possibility that it is simply some kind of technical error during observation, which is not so far-fetched, since subsequent observations did not yield encouraging results. However, as in the case of the giant satellite Kepler 1625b, an exomoon can be observed if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange, inclined orbit, like Neptune's moon Triton. Such an enormous size for a possible moon could become one of the most important elements in the search for other moons. Therefore, more than 20 exomoon candidates are currently known, all of them gigantic, probably at least for Kepler 1625b, the star around which it orbits, which is a red giant. This dying star can heat the moon's atmosphere, which would increase its effective diameter and allow scientists to detect satellites more frequently. However, perhaps at this time, exomoons do not have enough scientific importance for scientists to invest many resources in developing technologies to find them at this stage of our science. Exomoons do not seem to have a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have many possibilities of giving false positive results. So months or even years of observation and analysis may be necessary to confirm a satellite's existence, when it seems more rational to dedicate those resources to exploring a planet with the potential to harbor life, including human life. Of course, it is possible that exomoons hide life inside, but alternatives in the form of rocky exoplanets like Earth are still much more important in scientific circles. But let's focus on the moons themselves and try to investigate them. Is it really necessary to study these mysterious, hidden moons? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, although not in the near future. The first thing that catches the attention of scientists, even of simple exomoon candidates, is their size. The largest moon in the solar system, Ganymede, which orbits Jupiter, has a DI of 3,273 miles or 5,268 kilometers, but the recorded exomoons can reach the size of the Earth or even Neptune. Therefore, since these moons are even difficult to distinguish from exoplanets, it is incredibly exciting to imagine what these moons could be like and what activity they could present. It is possible that some large exomoons have many planetary characteristics and that their study could change everything we know about satellites. Their similarities with other exoplanets, such as their probable geological activity, lead us to the next important point for careful study in the future: the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could hypothetically be a refuge for living organisms due to the presence of global oceans. However, what about much more massive moons that can not only support a dense atmosphere, but also have more access to the chemical elements necessary for construction, both from the inside and from the outside? According to a study by the University of Washington, exomoons have more potential to harbor life than even exoplanets, since they also have a habitable zone, although is slightly different. But the main argument in favor of exomoons is that one of the most intriguing places for the existence of life is the availability of various heat sources. The first source is the star itself, and the second is its planet. The moons are heated by the gravitational attraction of the planet, which keeps the probable water inside the moon in a liquid state. In addition, the heat of an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time and also bring to the surface various crucial chemical elements. So exomoons are not as simple as they seem. Perhaps the difficulty of finding them will be rewarded with a potential advance in science. Finally, exomoons can become the necessary tool to study the formation of our universe. Since the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for sustaining life, and what is the history of other planetary systems in general. In particular, comparing the moons of the solar system with those of distant systems can provide scientists with an understanding of the particularities and conditions of their development, as well as an approximate value of the abundance of systems in which complex intelligent life has developed. The Earth, hypothetically, could be almost the only planet in which life could have formed, at least in the visible universe. And any clues about exomoons with potentially greater possibilities of harboring living organisms could confirm or deny this hypothesis. However, for now, in-depth exploration of exomoons is only a matter for the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time this decade will not disappear. However, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, it is likely that exomoons will become one of the engines of technological progress, since we know that the transit method or the gravitational lens will not help to look for microsignals of the presence of exomoons. So this factor already poses a challenge for scientists, who must modify or even create new technologies to capture such subtle objects. However, this is a task for the near future. In the long term, both the intriguing moons and the exoplanets will require a much more exhaustive analysis, including the use of images and samples of the atmosphere or even the soil. So, if interesting candidates are ever found where extraterrestrial life exists, it is likely that exhaustive space missions will be carried out that advance human knowledge in this field. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Platon mission, which will continuously observe several areas of outer space to capture objects in transit. The mission will last 6 years and could be the one that achieves this expected discovery. However, the benefits of the search and exploration of exomoons are not limited to technological advance. Exomoons are very valuable natural laboratories located near various planets and stars, and the analysis of the impact of these bodies on the moons will not only deepen what is known about the formation of planets, but will also demonstrate to scientists the variety of conditions in which life can develop. For example, traces of biomes or even the technological footprints created by civilizations on various moons can provide a clear picture of the indications of the development of intelligent life, which would allow establishing more priority routes for future missions to the planets or moons with the highest probability of harboring extraterrestrial life. But for now, we can only wait for the moment when we find the first exomoon and begin a long but exciting journey that will change scientific and technological life. Exomoons, despite their invisibility and skeptical insignificance, may one day crucially change everything that the human race knows about our vast universe. Even a small observation can end up becoming the main engine of revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the mysterious and cumbersome cosmos one day cease to be so confusing for us. But given the immensity of the universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our result may be. Let us imagine a colossal, invisible force controlling the galaxy's existence. This hidden director is none other than a supermassive black hole. Although often described as chaotic monsters that consume everything, these giants play a vital role in the life cycle of galaxies. In the center of most large galaxies lies a supermassive black hole whose gravitational force is so strong that not even light can escape it. However, they actually do more than absorb matter. They act as the heart and lungs of their galaxies, giving life to the celestial environment in ways we're just beginning to understand. Recent research shows that the jets of gas and radiation expelled by supermassive black hole poles are similar to the airways that feed our lungs. These jets create shock waves that oscillate in a manner very similar to the thoracic diaphragm of our chest cavity, which moves to inflate and deflate our lungs. This respiratory system helps regulate the growth of galaxies, preventing them from becoming too large and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how the heart and lungs of a galaxy, in the form of gas columns coming from a central supermassive black hole, can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be full in the form of columns of gas coming from a central supermassive black hole can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be full of zombie galaxies, enormous clusters of dead or dying stars. The shock waves generated by the jets of black holes can prevent the formation of stars by heating the surrounding gas and preventing it from cooling and condensing to form new stars. This process may seem destructive, but it is necessary to maintain the health and longevity of galaxies. Today we will try to understand the mysterious nature of supermassive black holes. We will learn the profound impact they have on the universe, and in the end, realize that even in the darkest corners of the cosmos, there is a heartbeat that connects us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, their types, and some key discoveries. Black holes can form in two main ways. The most common is associated with the death of massive stars. When a star with a mass between 8 and 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion known as a supernova occurs. The core collapses under its own gravity, forming a stellar black hole. These black holes usually have a mass several times greater than that of the Sun. Another way is the direct collapse of massive gas clouds, which completely omits the star formation stage. This process can lead to the formation of black holes with masses ranging from thousands to hundreds of thousands of solar masses. These direct collapses are believed to have occurred in the early universe and were the origin of the supermassive black holes we see today. The concept of a black hole was first predicted by Carl Schwarzschild in 1915 as an exact solution to the equations of These equations describe how matter shapes the fabric of space and time. The Schwarzschild solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape it. The first black hole confirmed by observations was Sagittarius X1, discovered in 1964. This stellar mass black hole in the Milky Way was identified by the emission of X-rays caused by the accretion of material from a companion star. This discovery was the first convincing evidence that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the limit beyond which nothing can pass. Once inside its limits, the photon sphere is a region where gravity is so strong that light particles are forced to orbit in the center. There is a singularity, a point of infinite density where the laws of physics, as we know them, are destroyed. Black holes come in a wide variety of sizes. Stellar mass black holes form from the collapse of stars and have masses several times greater than that of the Sun. Supermassive black holes, located in the center of most galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, less common, fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration captured the first image of a black hole located in the galaxy M87. In this historic image, the shadow of the black hole can be seen against a bright accretion disk. The observation provided direct visual confirmation of theories about black holes and opened up new possibilities for studying these mysterious objects. One of the most common and debated questions lately about black holes is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon. One falls into the black hole, and the other flies away for an incredibly long period. This trick of expelled particles can cause the black hole to lose mass and eventually vaporize. Although black holes are depicted in science fiction, they're not cosmic vacuum cleaners that indiscriminately absorb everything around them to hit them. Objects must get incredibly close to the event horizon. Furthermore, although it has been proposed that black holes are possible wormholes or portals to other universes, these ideas remain speculative and are not supported by any observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the fundamentals of black holes, how they form, their different types, and key discoveries, lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is noticeable due to the enormous gravitational forces they exert on their environment. But how do these colossal formations arise, and what are their defining characteristics? In theory, a black hole forms when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful that escape is impossible. This concept, which was once considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive ones, are scattered throughout the universe and may number in the billions. The supermassive ones, with masses millions or billions of times greater than the Sun, are detected by their gravitational influence on nearby stars. These stars orbit the black hole much faster than they would a normal object of similar size. By measuring these orbital speeds, astronomers can estimate the black hole's mass. For example, the black hole located in the center of our Via Lactea, Sagittario, has a mass of about 4 million solar masses. Some supermassive black holes even surpass Sagittarius A. The dwarf galaxy Leo 1 houses a black hole with a mass around 3 million solar masses. In a neighboring elliptical galaxy Centaurus A, there is another black hole with an astonishing mass of 55 million solar masses. Even more colossal is a black hole in the galaxy cluster AIL 2261, whose mass is estimated at about 100,000 million solar masses. Although its exact location remains unspecified, these black holes, especially in an active galaxy, behave differently, surrounded by an accretion disk of gas and dust that rotates rapidly and can emit enormous amounts of energy, sometimes eclipsing their entire galaxy. This same process was captured spectacularly by the Event Horizon Telescope in 2019, when it photographed the accretion disk around the supermassive black hole of Messier 87, revealing the ominous shadow of a black hole with a mass of 6,500 million solar masses. The formation of these supermassive black holes is a subject of intense study and speculation. Unlike the vacuum cleaners of science fiction, real black holes attract matter by gravity, not active suction. This gravitational attraction becomes unusually strong at short distances, but at greater distances, it behaves like the attraction of any object of similar mass. According to one theory, the oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds containing as much matter as millions of stars. This direct collapse model suggests that these black holes could have formed in as few as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes, born in the extreme conditions of the Big Bang, served as seeds for later growth. By studying these colossal formations, we obtain information about the fundamental processes that shape galaxies and, by extension, the universe. But what happens when two galaxies collide? It is not just a dramatic cosmic event, but a transformative process that changes the very structure of galaxies. At the center of these galactic collisions are supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable merger. This process is not silent, but sets in motion enormous amounts of ambient gas and dust, creating a turbulent environment conducive to extraordinary phenomena. Physicists have modeled these colossal mergers and discovered that, as black holes spiral closer, they can produce jets of incredibly energetic electromagnetic radiation that shoot out along the axis of rotation with much more power than normally observed around isolated black holes. The cosmic spectacle begins even before the black holes completely merge, offering astronomers a possible warning of these events. When these supermassive black holes finally collide, their jets combine into a single burst of high energy that may be accompanied by less directional bursts, increasing the chances of detection. The fusion process sets the surrounding plasma in motion, causing powerful jets that, in theory, can be observed billions of light years away. The detection of these cosmic events is not only exciting, but offers a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can reinforce the current understanding of gravity or open new avenues in physics that could lead to alternative theories. Future missions, such as the Space Antenna with Laser Interferometer, or LISA, promise to expand our ability to locate these mergers. LISA, a joint project of NASA and the European Space Agency, will orbit the Sun and detect the gravitational waves emitted by these mergers. The combination of gravitational wave data with electromagnetic observations will allow precise location and study of these events. Until these advanced instruments come into operation, astronomers depend on existing observatories to detect electromagnetic jets, which provide a dynamic view of the evolution of galaxies and demonstrate how these mergers can drastically change their structure and behavior. But let's take a closer look at Sagittarius A, which is 43 million times the mass of the Sun. In mid-spring this year, the giant of our galaxy revealed new secrets thanks to advanced observations from the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A, providing new insights into the magnetic fields surrounding this black hole. Polarized light is crucial for understanding these fields, as it shows how light waves are oriented and allows us to understand the properties of the gas and the mechanisms that drive the black hole's activity. Interestingly, the magnetic field around Sagittarius A are surprisingly similar to those observed around the much larger black hole in the galaxy Messier 87, which has a mass 65 billion times that of our Sun. This similarity suggests that strong and organized magnetic fields may be a common feature of all black holes, regardless of size. The presence of such magnetic fields makes intriguing the possibility that Sagittarius A may contain a hidden jet. In other black holes, these fields drive powerful currents of matter, although Sagittarius A appears relatively calm and consumes a minimal amount of matter. The similar structure of its magnetic field suggests the possibility of a weak jet that has not yet been observed. This new image of the black hole in the center of the Via Lactea tells us that there are strong, ordered, and swirling magnetic fields near the black hole, explains Sarah Issoun, co-director of the study and fellow of the Einstein program of the Hubble program of NASA at the Center for Astrophysics of Harvard and Smithsonian. These fields are crucial for the way black holes interact with the gas and matter that surrounds them. It was the EHT, a set of telescopes from all over the world, that made these revolutionary observations possible by combining data from multiple telescopes. The EHD forms a virtual telescope the size of the Earth, capable of capturing unprecedented details of black holes. Although Sagittarius A is closer, it presents a unique challenge due to its smaller size. The material that rotates around it moves quickly, making it difficult to obtain sharp images. In contrast, in the large M87, the material moves more slowly, making it easier to observe. Overcoming these difficulties has provided invaluable data to compare black holes at opposite ends of the mass spectrum. The similarity observed in the magnetic fields between Sagittario A and Messier 87 suggests that our galaxy's central black hole could have a hidden jet. If it existed, it would provide new knowledge about the behavior and evolution of black holes and the galaxies where they are located. The observation of this jet would be a great discovery that would relate Sagittario A with the energetic processes that form galaxies. The discovery of this jet would greatly expand our understanding of how black holes affect their environments. The jets can expel gas and dust, which affects star formation and the general evolution of galaxies. When comparing different black holes, astronomers will be able to identify the universal principles that govern these mysterious objects. The study of our own supermassive black hole allows us to root these abstract concepts in a familiar context, bringing distant space closer to home. The influence of supermassive black holes extends far beyond their gravitational effects. The relativistic jets can have a dramatic effect on the formation and evolution of the galaxies, affecting everything from the formation of stars to the distribution of the gas and the dust. A striking example of the influence of the jets of black holes is the Teacup Galaxy, located at a distance of about 1,300 million light-years from the Earth. The Teacup Galaxy owes its name to its peculiar handle-shaped structure, which formed due to the activity of a relativistic jet from its central supermassive black hole. This galaxy is a clear example of how even the low-power jets can significantly affect the environment, even in the case of the silent galaxies in radio. The jets can redistribute and disturb the surrounding gas, which will impact the capacity of the galaxy to form stars. Recent observations with the Great Millimeter Array ALMA have shown that the jets of the cusp galaxy, although relatively weak, move heat and accelerate the gas of the galaxy, even in the case of radio-silent galaxies. The jets can redistribute and disturb the surrounding gas, which affects the galaxy's capacity to form new stars, explains Christina Rouse-Alida, astronomer of the Institute of Astrophysics at the University of California in Santa Cruz. The effects of these jets do not always occur head-on. The study discovered that the most significant effects in the Teacup Galaxy occur perpendicularly to the direction of the jets. This lateral turbulence is caused by shock waves generated by the jet's bubble, which heats and inflates the gas. These interactions can prevent the formation of stars by preventing the gas from cooling and collapsing to form new stars, while the strong jets can heat the gas of the galaxies to such a point that they slow down their growth, preventing the formation of new stars. The weaker jets, like those of radio-silent galaxies, also play an important role. These jets can stir the gas of a galaxy, causing its movement and redistribution. This activity can give rise to the formation of new structures inside the galaxy and affect its long-term evolution. Understanding the influence of these jets allows the astronomers to reconstruct the complex puzzle of the formation of the galaxies. The supermassive black holes are an integral part of the life cycle of galaxies, from the dramatic changes caused by powerful jets to the more subtle but significant effects of weak ones. Stay tuned to explore together the forces that shape our universe. In the middle of the peace and the tranquility of the celestial bodies of the solar system, there is an object that greatly disturbs the peace of the rest, the moon Io. Unlike any other that orbits around the powerful Jupiter and wrapped in mystery, Io is a world of fire and fury, a marked contrast with the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces that act in the cosmos. Its surface, plagued with hundreds of active volcanoes, tells the story of the relentless and complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this burning world. Its mission is to unravel the mysteries of Io, capture its burning essence, and discover the secrets that have long remained hidden beneath its tumultuous surface. While Juno gets closer than ever in 2 decades, We find ourselves on the threshold of new discoveries and ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect the giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new spatial views. Juno, a spacecraft made not only of metal and circuits, but also of ambition and curiosity, embarks on a journey that is not